We're going to prove by induction the formula for the sum of the first n terms of a geometric series. So as we see here, our first step, step 1, is to show that it is true for n equals 1. So when n equals 1, we will just have a equal to n equal to 1, a bracket 1 minus r to the power of 1 over 1 minus r. 1 minus r is cancelled. We're left with a is equal to a, which is true. So it works for n equals 1. Our step 2 is to assume that it is true for n equals k. Therefore, that would look like a plus ar plus ar squared and so on, plus ark to the power of k minus 1 would be equal to a bracket 1 minus r to the power of k over 1 minus r. So we are assuming through for n equals k. Our step 3 is to now prove that it is true for n equals k plus 1. And that would look like a plus ar plus ar squared plus ark minus 1 plus ar to the power of k will be equal to a bracket 1 minus r to the power of k plus 1 all over 1 minus r. So to start our proof of this, we're going to first of all start with our assumption. So our assumption was that a plus ar plus ar squared plus ark to the power of k minus 1 is equal to a bracket 1 minus r to the power of k over 1 minus r. What we are going to do is we are going to add ar to the power of k to both sides of this. So if I do that, I end up with a plus ar squared ar squared of k minus 1 and r plus ar to the power of k is equal to a bracket 1 minus r to the power of k all over 1 minus r, and we're going to add the ar to the power of k there as well. Now we are just going to focus on this right hand side. So our right hand side will be equal to, if I bring it together, I need to add these together, so I'm going to bring it together in a common denominator. The common denominator being 1 minus r. So I will have my a bracket 1 minus r to the power of k, and then I'm going to have a plus a r to the power of k times by 1 minus r. So that's just bringing it together into one fraction with a common denominator. So if we multiply out what we have here, we'll end up with a minus ar to the power of k. We'll have a plus ar to the power of k and a minus ar. Here we have a power of k and a power of 1. Same base, so we add our powers, so we get k plus 1. And on the bottom, we will have 1 minus r. If I keep going with that and I tidy up what I have, our ar to the power of k and ar to the power of k cancel. One's a plus, one's a minus. So we're left with a minus ar to the power of k plus 1 over 1 minus r. If I factorize the top, I can take an a out, leaving me with 1 minus r to the power of k plus 1 over 1 minus r. And that's exactly what we needed to prove. So we can say that the proposition is true for n equals 1 if our assumption is correct. The proposition is true for n equals k, then it will also be true for n equals k plus 1. Therefore, by induction, it is true for all n being an element of natural numbers.